Hello, everyone. Thank you for joining us this afternoon for the second installment of the Early Career Researcher season as part of our Australian Geometric PDE seminar series this year. Today, I'm pleased to welcome Simon Goodwin, who's joining us from the University of Auckland. Simon is going to be talking to us about killing tensors on Riemannian manifolds. Thank you for that, Simon.
All right. No problem. Yeah, so today I'm going to be talking about prolongation, tractors, and killing tensors. Hopefully, it'll cover a decent amount of all of them. It'll be a bit meandering, but hopefully we'll get to somewhere interesting in the end. So, starting us off right at the start, killing tensors, of course, on a Riemannian manifold are, well, at least in the rank 1 case, are vectors which essentially generate isometries of the manifold. And so another way of writing that is that the Lie derivative of your killing of your metric along the flow of your killing vector is 0, or in much more algebraically manipulatable form, this, where here I'm going to be using abstract indices throughout. Little letters denote tensors, and when we get to tractors later on, I'll let you know what denotes them. So over here, we can see a fairly classic example of a killing vector is just, the isometries of the sphere are just rotations. So any killing vector, flows along the lines. I'm not going to say latitude, longitude because I'll get it wrong. So, however, this is obviously a PDE that we've got here for killing tensors. And it can be extended, and I'll be talking about higher rank later. In fact, you can give your killing tensor k indices, and then you simply symmetrize over all of the indices here. And so these brackets around my abstract indices are the symmetric part. You sum over all possible permutations and then divide by the number of permutations. And the immediate thing that we notice here is that this PDE is overdetermined. There's far more equations than there are unknowns. Even in the rank 1 case, we can see there's essentially n choose 2 unknowns here, but there's only n variables. There's only the n entries of our tensor, and so a natural way to approach this PDE is to study it via prolongation. And so prolongation is something that we can do to overdetermine PDEs, where we essentially introduce more variables to try and sort out our lack of variables problem, and hope that when we take their derivatives, we don't end up in a huge mess, and eventually we get to some sort of closed system. Now, I'll give a quick example, because this is the easiest one that I know to compute for killing tensors. If we consider a killing tensor which satisfies this equation here, then, if it's not going to tell me I have spelling mistakes, if we have its derivative, it must be antisymmetric, essentially by definition. And what we do is we essentially just make this a new variable, and then we compute its derivative. Okay. So the first step that we can write out is what we essentially defined it as, being the second derivative of our killing tensor. Okay. But now I'd like to write this in terms of curvatures, and so I'm going to add and remove something that's going to help me to eliminate certain terms. And so, of course, the first term that I've written here is simply minus the curvature on R. So on my next step, I get minus RAB DC onto RD. And then what I'm going to do is I'm going to play with this term on the right by using the antisymmetry of mu, or nabla AR. And so what I can rewrite that as I can now rewrite that as, well, minus nabla B, nabla C now on RA. And then, of course, what I can do is I want another curvature term, don't I? So I can add back in nabla C, nabla B onto R, and then subtract it away again. And eventually, after a while, I'll keep, stumbling through this. And so now I've come to my final term, and so when I do this one, I'm just going to cheat by looking over at my one I prepared earlier over here. A C D B R D, and then the last term is going to be minus mu A. Well, okay. The last term would be this, but I'm just going to immediately substitute back in mu BC over here. So what I have is I have what I had on the right-hand side again. Now I simply need to use the the Bianchi identity on one of these guys. And very quickly, I'm going to move that onto the other side and divide by 2. I'm worried about my time here, so I'll just keep cheating on the notes I have on the side. And so now what I have is that after this whole process is finished, the system has closed up, in that now I have another unknown, this mu, and its derivative is completely algebraically captured in terms of R. And so, okay, now that the simplest case I know of prolongation has managed to come to a nice end, we can then form essentially a bundle and a connection from this. So what we do is we simply take our bundle to be the one forms direct sum 2 forms essentially here. And so the 1 forms represent our R, and then we've got our mu is our essentially derivative of R. But what we can do is we can define a connection on this bundle like this, and it becomes clear that the killing tensors, well, the killing vectors in this case, become are in one-to-one correspondence with parallel sections of this bundle. And essentially the top slot of this bundle will be your killing tensor. And so this is a very nice way to understand these things. We can look at this bundle, we can look at its curvature, we can find parallel sections, and it's easier to work with. But there's some steps missing here, and one of those is that killing tensors are more naturally studied can be studied instead from projective geometry. As we're going to get to later, essentially killing tensors are projectively invariant. And instead of writing out our prolongation like this, we would much rather write it out in a projectively invariant way. So let's see how to do that. I'll begin by defining what I mean by projective structure. A projective structure is an equivalence class of affine connections, so connections on the tangent bundle, that have the same unparametrized geodesics. So if we think of, for example, our sphere from earlier, the geodesics are the great circles on the sphere, and we're looking for all affine connections that give us the same geodesics. They can speed up, they can slow down, they can turn around, but they have to still be those great circles when you look at them as unparameterized curves. Now, algebraically, this can be much more neatly written down, I would say, as this equation here for some one form upsilon. And so now this essentially gives us all the tools that we need to analyze things like projective changes and develop some calculus here. So while this is the transformation law for one forms here, we can of course calculate the transformation law for vector fields. We can calculate it for 2 forms or just covariant 2 tensors. And I've got an important one down here, being the K antisymmetric vector fields. It's going to come up later, but you can look at this transformation law, and you can look at tensor products, and you can say, okay, how should it expand? And you can expand it, and if you take your vector here to be antisymmetric, then what you get in the end is you get this equation here. And so all of these equations are my different connection inside the projective class as the original one plus something, right? Usually involving this upsilon. And they're going to come up again very soon. But for now, I'll just go into projective killing tensors. So, as I had before, killing tensors of rank K what I can do is I can say, okay, well, what's its derivative in one connection, and then what is it in another one, and how do they differ? And well, when I take the symmetric part, I don't end up with the same thing. So I've already encountered a problem. I told you earlier that the Killing equation is invariant, but it's not. So we're going to fix this. And we're going to do it by weighting our Killing tensor. Now, projective weights really are something that is quite natural when you look at it from the perspective of these transformation laws, but to construct them and to talk about these bundles, it looks a little bit complicated. But I'll go through how it works. From our equation that we had earlier, if we have an alternating n vector, now n is the dimension of the manifold, not any k, then what I find is that after a change of variables, I add n plus 1 of this epsilon onto v, and then I subtract n plus 1 times by this thing. And what we need to notice here is that it should just be b, not b1, but it doesn't matter. We've got n plus 1 indices here, which we're anti-symmetrizing on. And so this term vanishes. And so what we're left with is the connection on v, the hatchet connection on v is the connection on v plus n plus 1 times by on epsilon with v. And I'm kind of deliberately ignoring my indices now here, because what I want to consider is I want to just consider v as a function. Because this bundle that I've defined up here is actually just a line bundle if our manifold has dimension n. And in fact, I take its second power to ensure that it's oriented as well, even if m isn't. And what this gives me is it gives me an oriented line bundle for which I know the transformation law is just adding 2n plus 1 times by this thing. And what can I do? Well, I can form powers of this bundle, exactly how to do this. You know, you have to kind of do it your favorite way, but there are various ways to do this. And what you end up with is you end up with oriented line bundles for every weight in the real numbers. And the transformation law is simply this. And this is going to help us because what we can do is we can add a weight to other tensors or later tractors or whatever we feel like by essentially taking the tensor product with our weighted bundle. And so because of the way the connection must act, whatever transformation law we had before must simply, we just add w times by our, well, there's an epsilon missing there. We simply take w times by whatever we had, whatever weighted thing, and then add that times epsilon. And so now we can fix our projective killing equation. What I'm going to do is I'm going to put a weight in here. I'm going to put a weight in to k. And so now what do I get here? Well, I can add now to k times by epsilon a, a1 through ak. And what do I get now? Well, this of course perfectly cancels this term that I had on the right-hand side, and voila, my killing equation is now projectively invariant. Wonderful. And so now I can start to consider studying these things from the perspective of projective geometry. However, the full machinery in order to produce my prolonged system involved the use of a connection, right? The first thing I did was I said, okay, well, let's take a connection and let's compute what its killing tensors are. And then I computed the connection on R, and I went on and so forth. But the problem when I've gone to projective geometry is that by design, there is no distinguished connection on the tangent bundle anymore. So what can I do? Well, there's this wonderful machinery that I can use called tractor calculus. So of course I've got to get a little bit of this in here. And so what I'm going to do is I'm going to set up the projective tractors and then tell you how we can use this to prolong our killing equation. So in order to define our tractor bundle, I need these weighted functions, and I need their jet bundles. And so there's probably put a 1 on here. This is meant to be the first jet bundle of the weighted of the 1 weights. And so this is what I call our co-tractor bundle. And we can see that, and we'll see later why we're starting here, because the setup in the conformal cases takes a little bit more, a few more steps. And so what this does is it fits into the first jet sequence illustrated here. What we have is we have one forms, and so from our one forms you can form functions which have certain derivatives around a point. And so I suppose I should say our one jet bundle here is simply the bundle of equivalence classes of functions at a point that agree up to their first derivatives. So it's this, you have a little bit more information here about your functions. And so there is, once you kind of write everything out in coordinates, it's kind of obvious that there is, but it turns out to be invariant of whatever coordinates you choose, etc. There is this natural inclusion here of one forms into one jets, essentially encoding functions derivatives. And then the easier map to describe here is this right-hand map, which takes a jet of a function and gives its value. Okay, so that's the easy one. And so what we can then do is well, we call this the tractor bundle, and I've written these weird z's and these weird x's. They have uppercase indices, and so what I'm using for tractors, if it's a co-tractor, it has a lower capital index. If it's a tractor, it has a capital upper index. And what this z lower a upper a says is it says that it takes a one form and it gives us back a tractor. And this x on the right here is saying that it takes a tractor and it gives us back a function. Of course, these have weights on them. But what we can see is that actually, if you choose a connection in our projective class, well, I just told you that connections can act on weighted functions, and it gives us back, of course, a one form on those weighted functions, or a weighted one form. And so it only uses first order information and is completely defined by that first order information. So therefore, this does give us a well-defined map from the first jet bundle into the weighted one forms. And this gives us a splitting of this exact sequence. And in fact, what we write for this is we give them other names. We call this one W. And of course, if we split on the left, we can then split on the right. And this one is called Y. And so our Z and our X are inherent on our manifold. We don't even need a projective structure to define them. They're just defined by this canonical exact sequence of the jet bundle. And the W and the Y depend on our choice of connection. And so given one of these connections, our tractor bundle now decomposes as a direct sum of our weighted functions with weighted one forms. And the structure that is kind of implied by all of this splitting that depends on the connection is that if I change the connection, it actually splits in a different way, right? And so, well, how did I say it split? I said this W is essentially just the connection, and since it's on one weighted things of weight one, what do we expect to add when we change our connection? Well, we add epsilon A times by sigma. Okay, so now we have a canonical bundle. Of course, there's many stories of how you can construct this bundle. It comes from Cartan geometry. It's a natural bundle. It probably some of its powers come from prolongations of certain systems. Of course, we're going to see one later, but it's totally natural in certain ways if you want to look into parabolic geometries. And of course, the thing that it comes with, when you look at it from that perspective, is a connection. It's not quite as obvious to us right now where it comes from, but here's the formula for it. We have the projective tractor connection, which is given by this formula on the right-hand side. And I have a couple of special curvature things that I brought up here, and they're not too important to our story, but they're listed on the right-hand side. The vial, the projective vial, trace free, and the beta here is in case our connection isn't torsion free, it's anti-symmetric. But those things aren't too important to what we're talking about. But what we do want to look at is the curvature of this connection. and it's usually denoted by a little kappa, and it has components essentially this Weyl curvature and this thing called the cotton tensor. And projectively flat will mean when w equals 0. If your dimension is at least 3, then that gives you cotton equals 0 as well. Okay, now that we have all this set up, we can actually start to prolong our killing equation. So what we do is we first take our killing tensor and we embed it into tractors. So this thing had weight 2k. Each of our z's, because they're going from a one-weighted bundle to an unweighted bundle, this tractor bundle, that's important. The tractor bundle, even though it's the jet bundle of a weighted bundle, it doesn't have weight, at least we consider it not to. And so each of these z's essentially subtract one weight from it, and so we have k over here instead of 2k. And now we have a fully symmetric tractor. Okay, great. Now we've put our R into tractor land. Now what can we do with it? Well, we have this thing called the Thomas D, which in the projective case acts a lot like a connection, really. On tractors, it satisfies Leibniz, and it here it decreases the weight of tractors by 1. But the important thing for us is that it gives a good oh, there's no equals 0 on the right hand side of my equation. The important thing for us is to essentially capture this in tractor world. And so what we can do is we say that, okay, if we apply D to our kind of half prolongation, we haven't quite fully prolonged it yet, but we're halfway there. Then this is equivalent to this condition down here. Okay. We can have a quick look at the proof here. And really, the reason that I've written all this out is to kind of demonstrate one of the nice things about tractors, which is that you can essentially capture most things you want to know by a few transformation rules, right? Which I hid in the corner up here. It tells you how you differentiate x, y, w, y, and z, and then you kind of have rules as to how these things go together. If you put w onto y, you get 0. If you put w onto x, you get a delta. And essentially, with a few short rules, you can even train, a graduate student such as myself to do these sorts of things. And all of the calculations here just follow from those relations. And so, in the end, we get the proof of what we want, it being that essentially this derivative is just the same as embedding our symmetrized derivative of what. Okay. Essentially the same as just embedding the symmetrized derivative of R into tractors. I probably need another Z there, but it's not perfect. And so perhaps it's Y. Anyway. But the point is that you can kind of carry out these things fairly computationally, and there are even packages to do this sort of thing. Okay, but I mean, this equation's nice, but there's still a couple problems with it, right? It's not just a connection. It's not just a differential equation. Well, it is a differential equation, but there's this symmetrization on it, right? This isn't really like our prolongation connection we had before. That was just a connection acting on a bundle. So what are we going to try and do? Well, we're going to differentiate it some more. What we do is we form what we essentially call the full prolongation here. And I'm going to stick in this case to when we're projectively flat. So there is a story of this outside of projectively flat. It's a lot more complicated, and I'll touch on it briefly. But projectively flat makes things a lot easier to understand. And so because projectively flat means that our tractor curvature is 0, if we have two tractor connections, they commute, and it's fairly immediate to show that that means that these two of these D operators also commute. And so what we can do is we can apply k derivatives onto this R, and we get something with k symmetric derivatives in the front. Sorry, k symmetric tractor indices on the front because they're all just D's. and then k symmetric things on the end because our R was originally symmetric. And moreover, if we're killing, then if we symmetrize over any k plus one of these indices, we get 0. And so this is essentially just a fairly familiar Young diagram symmetry where you have two rows of k boxes, and it's this irreducible representation of GL or SL. And so that's the kind of tensor that we have. Right. And then of course this thing is we've managed to arrive in weighted 0 land. There's no weight on these things. And so actually we take this derivative and it's just z applied to this derivative, and it turns out that's 0 if we're killing. And so there's a fairly short argument here. If you can use a little bit of representation theory, essentially what we have is we have something that's symmetric on k plus 1 indices here and symmetric on k indices here. But when we commute over these ones, we get 0. And so you argue using these symmetries and kind of Young diagrams and tensor products that you must have 0 here, right? That's if we're killing, because killing is equivalent to symmetrizing over these last k plus 1 getting 0. And so now we end up with our theorem, our full prolongation. There's a one-to-one correspondence between rank k killing tensors and parallel tractors of this form with this Young diagram symmetry, with the last k, any symmetrization on the last k being 0. And this is actually kind of stronger than what we claimed before, because not only when we prolong do we get something that is parallel, if we do the opposite, we start off with something parallel, and the inverse of this one-to-one correspondence is a lot of z's onto s. Oh, sorry, z's and y's, w's and x's. I'm not sure, but essentially you project a load of these indices and you get back your k. And we call this the full prolongation. And this is essentially a higher rank analog of what we had at the start. Briefly, like I said, we can touch on this for curves for non-projectively flat. Our d's don't commute anymore, and so instead of just taking this as our full prolongation, we essentially project onto this component of the two-kth tensor product. And what you get is you get something that's no longer parallel, but it's parallel for a connection, right? So the details of this are in a lovely paper by Rod Gover and Thomas Leisner, titled "Invariant Prolongation of the Killing Tensor Equation." And so far, I'm only discussing their work, but I'll get to something that I can apply later. And so, looking at the rank 1 case, we can actually, of course, when it's flat, this star equation just says 0. Oops, this star equation just says 0 on the right-hand side, because it's parallel. But I can actually calculate this. Well, they actually calculated this Q thing here. And what you get, okay, so what is this? What is the connection here? Well, it's this thing on the right-hand side, but when you unpack these curvatures, what you will find is that you've essentially gotten back to what we started with. These are essentially equivalent ways of capturing the same thing. But of course, this tractor version has the added benefit of being totally projectively invariant. Everything is completely stated in terms of tractors. This the W and the E on here, even though the W isn't canonical when it transforms, I believe this one will stay. Yes, this one will stay projectively invariant because this one transforms with X and this is anti-symmetric. But that's the story here, that we end up with something totally projectively invariant. And so now that's a lovely story to finish everything off in projective world. I'm going to now try to go over to conformal geometry, in which we have a slightly well, we'll find out later, it's quite a lot more complicated version of what's going on, but hopefully we can see the analogs and that it's fairly similar in essence. So on to conformal geometry. A conformal structure is an equivalence class of metrics now, where they essentially differ by a positive rescaling. And so, of course, if you're talking about general relativity, these are the things preserving space-time structure, etc. And so this is a very natural thing. Conformal geometry, yep. We can now, but okay, right. We have a similar set of transformation laws because, like in the projective case where I had two connections, what I can do here is I can form a Levi-Civita connection of G hat, and I can form the connection of G, and I can say, well, okay, how do they differ, right? And so I get, in essence, very similar types of transformation laws, but they differ very importantly. And so I again use upsilon for this one form that kind of defines all of my transformations here. And it's this kind of log derivative of our rescaling factor. And okay, on one forms, we rescale like this, very similar to the projective case, but we've got this, which will come up again later. And I'm not going to go through the full story of conformal weights, but if you calculate the transformation law on n antisymmetric vectors, right? So it's not actually written here, but this is for n antisymmetric vectors. You will get this transformation law, and so okay, instead of having 2n plus 2, now it makes sense to essentially set this to be our weighted bundle of weight 2n. Of course, we square it again to make it oriented, and we take roots of it to give our other weighted bundles. And so we end up with weights again. Of course, this is W and this is omega, this is obvious. And an important other structure that we have here is we have what we can call the conformal metric, because there's a slight question later on. I start raising and lowering indices, but I'm doing conformal geometry here, so I don't really have a metric that's canonical. So how am I doing that? Well, I'm using this thing, and essentially what I do is I give my metric weight 2. And so there's an alternative way of seeing weights in which this is totally obvious, because weighted functions are essentially things which rescale as the metric does. So another way to define these weighted things is to have essentially you function, and then whenever you change your metric, you change it by omega to the W. This is the kind of natural way to see weighted functions. And I mean, that's essentially what's going on here. It's just a more explicit way of defining it. And so, of course, if we rescale our G, then it picks up an omega squared, so it naturally has weight 2. And the way to define this in this world is to look at the volume form and, well, I suppose if you're oriented, but there are ways to do it, to choose which one you want to do. But you can choose a canonical section of this weighted bundle. And now what we have is we have actual metrics are given by sigma to the -2 conformal metric, where sigma is some one weighted thing. And so because this has weight 2, this weight has weight 1, then these essentially annihilate the weights on G. And all of my underlines here, in LaTeX, they would look like bolded, because that's what's used. But here it's just the line underneath. So, all right. Conformal killing tensors, getting to the meat of the conformal geometry here. What we want to do is we want to again look at the killing equation. Let's take a symmetric K tensor, and in this case, I kind of know I'm cheating a little bit. I know that I'm going to give it weight 2K. And so when I write out my transformation law, there should be a -K here, but it turns to +K because of my weight. And I subtract, I add all the relevant things, and well, okay. Another problem here, because previously I had something that was projectively invariant, but well, now it's not conformally invariant. I have this kind of annoying term on the right-hand side, but what I can do is I can look at this and I can say, well, this is something in the metric. What I can do is I can take the trace-free part. So there's kind of a canonical way of doing this, if you have something with only two indices, it's kind of obvious. You trace it and then subtract whatever that is times the metric. If you've got k indices, you have to do it, well, more times, but you can fairly easily define what it means to take the trace-free part. And of course, that kills anything with g's on it, or deltas, essentially. It kills this part, and so now I have a conformally invariant killing equation. It's a weakening of our original killing equation, of course, because if we had something that was actually killing, then it would satisfy this as well. But I'm going to make the extra requirement here that my tensor itself should be trace-free. And this is what leads to the kind of best way of looking at this. And well, I've tried to do this this prolongation without tractors. There are a few too many variables for my liking. It's probably fairly easy to do, but we're going to look at the rank 2 case here, in which case I would say it'll be much less fun to do. But even the rank 1 case has all sorts of difficulties that don't appear in the projective case, in the just killing case, because you have all these traces and so on. So we're going to skip straight to tractors. As I mentioned earlier, the conformal tractor picture has a lot more steps that make it look almost less natural, that make it look strange. What's going on? Of course, this arises naturally from the perspective of parabolic geometries, and you can recover this. This is equivalent to the Cartan connection on for a certain parabolic geometry, and all this makes sense. But the way that I'm going to look at it, because it'll come up later, is that we actually form the tractor bundle as a quotient of the second jet bundle, which fits into this sequence here, kind of defined similarly to our first jet bundle. But what we notice actually is that this thing on the right-hand side is actually the projective tractor bundle, and that's going to come up later. And so now what we do is we have our conformal co-tractor bundle. We have to quotient here by some sub-bundle of this thing on the left-hand side, the trace-free parts of weight 1, and what we get is well, you kind of quotient this sequence out by that. Of course, it lies in the kernel of this map, so this part doesn't change. But in the middle, we get the conformal co-tractor bundle, and on the left, we get things of weight -1. So I suppose really this should have a weight 2 on it. But anyway, the important thing here is that this gives us a full trace of our tractor bundle in terms of now 3 subbundles. In the projective case, it was kind of obvious. We just had this bit on the left, but now we've got an extra part. There is, in fact, a nicer way of looking at this tractor bundle, and it's probably the first way that it'll be introduced if you're looking into these things. Is that actually? Nope, that would be on the next page, because it arises as a prolongation bundle. But also I've forgotten that I need to talk about all these things. So in conformal tractors, in projective tractor land, we had certain rescalings. How did our decomposition change? Well, if you choose a certain metric, then it splits our tractor bundle in a way that I'll get to on the next page. But it changes like this. So these things are fairly important for calculating in this tractor land. And now instead of having four things, we had x, z, and w, x, z, y, and w in the previous projective case. In this case, we just have x, z, and y, because we're saved by being able to raise and lower tractor indices using this metric on the right-hand side. And so our x is invariant. It should have an index, but it's invariant. Our z is not, unlike projective land, and then our y is also not. But this metric over here is, and so that's very important to us later. And whenever I raise and lower tractor indices, I'm doing it using this h on the right-hand side here as well. Now, how does this thing arise naturally? Because I just kind of had to say what everything is. I had to say what my projectors are. I had to say what my connection was. Well, I had to say what my decomposition was. There's a slightly more natural way of looking at this, which is to ask, I have a conformal structure. Are there any Einstein metrics in my projective class? Well, it turns out that you can essentially write this as a PDE that I've written out here. And so this row is a slightly different to our projective row before, but again, it's captured by what's on the right-hand side here. This W is trace free again. And so essentially, if I have a solution of this thing, then I form the metric, and I believe it's always Einstein where it's defined. I don't think there are any extra conditions on that, but definitely if you have a sigma which is non-zero everywhere, then this metric on the right-hand side is Einstein. And I could give the full prolongation of this one, but it's a little bit longer than the killing one I had before. And what you get is you get this thing here. And haha, this looks like something that could live in tractors. I have this sigma, this mu, and this rho is essentially a conformal Laplacian type thing on this sigma. And what I end up with is a prolongation connection. This thing, which in turn it turns out to be what we define as the tractor connection, which of course could have come from this Cartan and parabolic land, but instead we derive it here. And if we did have an Einstein scale, then essentially these three slots decompose like this. Like I said before, this is some sort of conformal Laplacian on our sigma. And this is what we're going to get as our D operator in conformal land, and this is what we call a scale tractor, which would be important very soon, because I'm going to have to get through these last few slides quickly. But I want to touch back on one thing I mentioned before, because when we define this conformal tractor bundle, I observed that the thing on the right-hand side here was just the projective part, right? And there's actually a reasonable way to look at both of these things. If I start with a Riemannian manifold, even if I don't assume Einstein yet, I essentially have a conformal manifold and a projective manifold, right? I could take the conformal manifold and given by the metric, and I could take the projective manifold given by the Levi-Civita connection, right? And I can say, well, is there any link between the projective tractor bundle and the conformal tractor bundle? And it turns out that if we're Einstein, then there is. And there's a map between the two given by this. And what it does is it maps into I perp. And the interesting thing is that if I write it out on this sequence above, my F here, mapping into here, so these are essentially totally natural invariant maps. This one's X, and this one is some sort of projection. If I write my F here and I split it on the right-hand side using this thing, this is actually the splitting given by when this map is contraction with I. So essentially this map on the left-hand side is just take a tractor and put I on it using our tractor metric that we had before. This will give you a -1 weighted function. And if we split it, and if we split our thing on the left like this, then the splitting on the right becomes a connection preserving isomorphism, if we're Einstein, between our projective tractor bundle and our conformal tractor bundle, which is very interesting. And it's going to give us a good way to look at prolongations just in a moment. And so there's actually a link here, if we're Einstein. If you're not Einstein, of course, you can still define this F on the right-hand side by letting it split this exact sequence as corresponding to I. And it gives you a map, and it still maps into I perp, obviously, because this needs to be exact. But it won't be connection preserving. But there may still be things to kind of pick up here and look at, and that's kind of something I'm still looking at. But if it's Einstein, then it actually gives the same connection. The projective tractor connection goes to the conformal one. And so now we'll look at conformal prolongations of killing tensors. But I'm going to stay in conformally flat land here. Before I was projectively flat, and then I mentioned the curved case here. I'm not going to touch on that. So when we're conformally flat, what we have is we have the Weyl curvature is 0, the cotton tensor is 0, because those are the slots of our tractor curvature. And the important things for calculation is that our tractor connections commute and our D's commute. And our D here is actually defined more generally for all tractors by this formula here. Again, a little bit more complicated than our projective version. And this one doesn't satisfy Leibniz, but it satisfies something similar. But it's a totally invariant differential operator, but here it's second order because it has this conformal Laplacian type thing on the right-hand side. And so what we can do is, let's start with rank 1. If we take a conformal, so because it's such a meandering route, I'll give a little reminder of what that equation was. That was essentially saying the trace-free part of this is 0. And what we can do is we can take this vector, we can plug it into a tractor, and we apply D to it. Looks very similar to our projective case. And we end up with an equation that this one is parallel if and only if this one is killing. Which again gives us a full prolongation. So we have a full prolongation for killing vectors. But now we have an extra question in conformal geometry, because what we're interested in, or what we may be interested in, is there a scale or a metric, G, you often call a scale, for which our conformal killing tensor is actually killing for our metric, because that's definitely something that could happen. It's always something times the metric, but it could be 0 times the metric, right? If we have such a metric, then it's called a killing scale. And the wonderful thing about our prolongation here is it allows us to capture that algebraically. Here I have this equation in terms of I and DI, but as explained before, our conformal tractor bundle essentially comes from prolonging the Einstein equation. So if I is Einstein, then this is actually 0, and it just says that I into k equals 0, in which case it's something just, well, it is anyway, something purely algebraic in terms of our prolongation. And this fully captures whether k is killing in the scale sigma. But one extra interesting thing is that if our scale is Einstein, then actually our k filters through this map F that I mentioned before between our projective and conformal killing, our projective and conformal tractor bundles. What you can do is you can form this prolongation here, and you can put it through to conformal land, and you actually get the conformal one. It's actually kind of obvious to see this once you look at it. But it actually opens up a little bit more when we look at the rank 2 case, which hopefully I have a couple more minutes to discuss.
Yes, that's fine.
Wonderful. And so in the rank 2 case, which actually is where I finally get to something that I've contributed to this whole story. In the rank 2 case, not yet though, we prolong instead to something with 4 indices. The story is a lot less clear than the projective one. There's a lot more steps here. We have to, instead of just embedding this with z's, we have to put on these extra terms, which are divergences and other extra terms, but we end up with some sort of tractor, and then we take 2 d's on it. That part's still the same as the projective version. And what we end up with, and here we're still conformally flat, by the way, we end up with something with Weyl curvature symmetries. So that means that it's anti-symmetric in the first 2 indices. No, sorry, this one is symmetric in the first 2, symmetric in the last 2. If you symmetrize over any 3, you get 0, and if you trace it, you also get 0. And now, because it's rank 2, we are essentially looking at this Young diagram for our symmetries, and there are essentially 2 versions of this. This is the symmetric version. You can fairly easily transform it into something with more familiar curvature symmetries, aka something that's anti-symmetric in the first 2, anti-symmetric in the last 2, and satisfies the Bianchi identity. In rank 2, it's kind of, you can do that because this looks like a square. And I may be referring to either one in the next slide. And of course, the important thing, what's our connection? What's our prolongation connection? Well, it's just the tractor connection. So W is parallel if and only if the top slot, so-called, is killing. Now there's actually 2 questions here at the end, because tensor, you actually have 2 questions. First, it could be killing. Second, it could be the trace-free part of a killing tensor for our metric. if it's killing, then there's this wonderful characterization of it. Well, if it's a strong killing scale, which is this first one, if and only if I into W is 0. In this case, again, W equals F of R, where this is the projective prolongation. And last slide, if we're Einstein, just have a look at the last bit, then we have this wonderful algebraic condition here. This is equivalent to being a killing scale, which is really amazing because this allows for a trace adjustment as well as being killing. And all of that is captured just by this scale tractor onto our full prolongation and some anti-symmetrization here. And in this case, still the Einstein case, this W ends up being the trace-free part of the R where we push it forward using our familiar F from the projective land. And the equation at the top is one that is actually something that I managed to contribute, which is in the non-Einstein case, everything looks a lot more messy, but we're hoping that it still gives something interesting. Yep, I think that's all I have to talk about.
Thank you very much for taking us through that, Simon. Everyone, let's thank our speaker. Now, does anyone have any questions or comments or maybe even feedback for our speaker?
That would be nice too.
All right, well, I have a couple of perhaps naive questions. The first, I suspect you would have answered this somewhere in your talk, but maybe I wasn't paying attention. I presume this theory is quite vacuous in dimension 3 because you talked about parallelicity of the Weyl curvature tensor. But of course, the Weyl curvature tensor vanishes uniformly in dimension 3, and so it's parallel then, presumably.
Yes, nearly. The thing is that actually, because we're talking about the W is slightly misleading. This W is this prolongation here. It's not actually the Weyl curvature.
Yes.
And so actually in dimension 1, you would have a very good point because this this conformal tractor bundle, if I can find my decomposition here, has rank n+2, right? And so if we are in dimension 1, then of course it's totally
yeah, okay.
We don't have anything. You can kind of look at those things still in dimension 2 or 3 because you still don't have many curvature tensors and you can start to do things a bit more explicitly.
Yeah, okay. One more question before I go on to a question from the chat. This is very forward thinking, but do these techniques, you mentioned Einstein a lot, could these techniques be used to either construct new Einstein metrics or else say new things about ones we already know about?
What does this allow us to say about Einstein metrics? Of course, the conformal tractor calculus is very useful for looking at Einstein metrics and this Einstein equation or so-called almost Einstein because it allows for singularities is very important to looking at whether there are Einstein metrics in the conformal class. It's very fundamental to trying to study those things. In terms of killing tensors, well, it can be interesting to ask whether there are Einstein metrics for certain killing tensors and so forth. In general, I don't think it would give you other things, but perhaps I'm not sure. But definitely the tractor calculus in general is definitely very, very applicable.
Yeah, I don't know. For example, I had in mind, could you? The answer to this is almost certainly no. But could you use this to say, here's an Einstein metric we already know about, and here are some symmetries that we didn't previously know about for this particular Einstein metric, but that sounds a little too good to be true, perhaps.
I don't know. Rod would have to answer that.
Yeah, rightio.
I have to fall back on my supervisor for that, but
yeah, not to worry.
I'm sure he'll let you know if it did. Wow, I see quite a few things here.
Yes, I don't know. Rod's been answering some of these for you, it seems.
Oh yes.
You want to
thank you, Rod.
Have a quick read through these questions and see if you have anything you want to add.
Yes, I can give all the references. They should have been given in the talk, really. That's my fault. The projective stuff, as I mentioned, is in a paper of Rod and Thomas Leisner's called Invariant Prolongation of the Killing Tensor Equation. The conformal Killing prolongation is in a paper by Rod, Jonathan Kress, and Thomas Leisner called Conformal Killing Tensors and Their Killing Scales, which I believe is on Archive. For now, and there are a couple of papers by him and Heather Macbeth, which have been very helpful in writing this talk. But do I have them on hand? He's probably already provided the reference, so I'm going to hope that he has. One of them is called Searching for Einstein or something like that. Detecting Einstein, Geodesics, Einstein metrics, and projective and conformal geometry. And that does in fact cover this conformal to projective mapping. And so does the one with Thomas and Jonathan. But I believe that probably those references are already been discussed. Let me see. What do we have after that? Interest in applications to mean curvature flow and conformal geometries. Have you any applications to induced conformal structures on submanifolds? Well, specifically for the killing stuff, I'm not sure, but submanifolds have been kind of a focus of different students of Rod's. I've heard many things about conformal submanifolds and projective submanifolds. And the induced structures, I mean, these are all things which are definitely very linked to these tractor connections. I don't know if I could give exact references for them. But a good starting point for any of this stuff, which I actually think does cover conformal submanifolds, is Sean Curry and Rod Gober's wonderful exposition of conformal tractor calculus, which will come up if you search Curry, Gober, and conformal geometry. But as far as the killing tensor connection, which is the focus of my stuff, which I eventually got to, I don't know if that would really have applications to that or not. Hopefully that covered what was being asked.
Yeah, great. Any further final comments or questions for Simon? Well, in that case, let's thank Simon again for all this, for his excellent talk.
Thank you.
All right, thanks all. We don't have a talk scheduled next week, and in fact, we're still looking for speakers. So if you're a postdoc or an HDR student and are anxious to give a talk, please do let us know. All right, I'll stop recording there, everyone. Thanks for joining us.